Hi everyone, hope all of you guys are doing well, and let's go ahead and do our experiment 4 post lab. Okay, so for the first part, a determination of pH by the use of acid base indicators, it's just you have to write down the information based on the video, which you can do. So I'm not going to explain that. Okay, there are several indicators given with the solution, so you have to write down what is the color and also the pH range. Circle the observations for each solution that was most useful in estimating the pH range. Okay, so you can just write down the colors. And then the part B, measurement of the pH of some typical solutions. Record the pH and color observed with bromocresol green for each of the 0.1 molar solutions that were tested. Record the pH. So you have to see the virtual video and you will see the pH is indicated here, but to write down the color you have to watch the video. Okay, so you will write down the color after you watch the video. pH for sodium chloride. Now sodium chloride, we all know that is a neutral salt, NaCl, so it should be basically 7, but it is pretty much close to 76.91 neutral. And sodium carbonate 11.15, meaning that is a basic solution. And then the third one, sodium acetate, which is 7.66, little basic. And sodium hydrogen sulfate 1.68, pH is very low, meaning that is an acidic solution. And it is asking some questions for any two solutions having a pH less than 6 or greater than 8. Write a net ionic equation to explain qualitatively why the solution has that pH. Now the first one is sodium chloride, which is 6.91, close to 7. Sodium carbonate 11.15, which is basic. Sodium acetate 7.66, which is also basic, and sodium hydrogen sulfate acidic. Now let's look at what is happening when these solids or solutions put it into water. What is going to happen? What kind of a dissociation is going to take place? Now I will explain you all 4 of these for you guys, but let's look at sodium chloride. What's happening with sodium chloride? Now sodium chloride, NaCl, is going to dissociate. So it is a ionic solid. It will dissociate into sodium ions and chloride ions. Now remember, you may have already learned in your lecture that the sodium ion is a cation from a strong base, which is sodium hydroxide. Let's look at how the sodium chloride salt is being made. If you were to make sodium chloride salt, you would use sodium hydroxide and hydrochloric acid to form sodium chloride and water. Now the sodium Na+1 cation that comes from a strong base, sodium hydroxide. Okay, and the salt, we have chloride ion and ion, come from a strong acid, hydrochloric acid. So if the salt that we are talking about, cation come from a strong base and an ion come from a strong acid, they are going to be neutral salt, meaning sodium and chloride, once the ions are being formed in the solution, they are not going to react with water to give strong acid and strong base again. What I mean by that, let's say you have sodium ion. Now this is in a water medium. So with sodium with water, what can happen is it can form sodium hydroxide. Okay, excuse me. Now sodium hydroxide is a strong base. So sodium ion will not react with water to give you sodium hydroxide, because in a strong basic solution, sodium hydroxide, we will not find sodium hydroxide intact as a base. Is going to dissociate into sodium ions and the hydroxide ions. So sodium ion will not react with water to give you sodium hydroxide. Okay, so sodium will remain as sodium. Same thing with the chloride ion. Chloride ion, that dissociated chloride ion right here, will not form a strong acid, hydrochloric acid. So as a result, once the sodium chloride ion dissociate into sodium ions and the chloride ion, they are not going to react with water to a considerable amount, so they're going to remain as a neutral solution. That's why the pH is 7. So any salt made with a cation from a strong base and anion from a strong acid, those salts are going to be neutral. Another example would be potassium chloride, KCl, because potassium coming from a strong base, potassium hydroxide, chloride coming from strong acid, hydrochloric acid. Similarly, potassium nitrate, potassium come from potassium hydroxide, nitrate come from strong acid, nitric acid. So that's how you're going to look at whether a salt is going to be neutral, acidic or basic. But in this case, this is a neutral salt. Okay, I'm going to go ahead and erase all of this. And then the next one we had was sodium carbonate. And sodium carbonate, the pH is 11 point something, right? Let's say 11.5. Let's go back and see. 11.15. So sodium carbonate pH is 11.15. But why it is 11.15? Right? Let's look at our sodium carbonate. So if you take sodium carbonate, Na2CO3, what's going to happen when this dissociate in water? Sodium carbonate, again it's an ionic solid, is going to give you sodium ions and carbonate ions. Once the salt dissociate into ions, we're going to look at to see if the ions dissociated excuse me, going to react with water. Now sodium ion with water, what is going to happen? Sodium ion, again, how does the sodium ion come? It comes from a strong base. It's a cation of a strong base, sodium hydroxide. So a cation from a strong base is not going to react with water to any appreciable amount. So nothing happened to sodium. Sodium will not react with water. Once the sodium carbonate dissociate into ions, it just stays in the solution. What happened to carbonate? Now carbonate is coming from a carbonic acid. Carbonic acid is a weak acid. When it dissociates, it gives you carbonate ion and hydrogen ions. But we can also consider carbonate coming from hydrogen carbonate. Now carbonate, since it's an ion of a weak acid, if it is an ion of a weak acid, it's going to react with water. If it was chloride like the previous one, chloride is coming from a strong acid, an ion, chloride will not react, but carbonate is an ion of a weak acid, so that is going to react with water. So carbonate will grab a proton from water and form HCO3 minus bicarbonate ion. Now the water HOH, right? One hydrogen taken by carbonate and then OH is left, hydroxide ions left. Now what happened? Once carbonate react with water, what is it adding to the solution? It is adding hydroxide ions to the solution, bicarbonate becoming bicarbonate anion. So hydroxide is a strong base. So as a result, since it is adding hydroxide ion, what do you think the pH going to be? It's going to be greater than 7. It's a basic pH medium. So that is why the pH is 11.15, since it is adding hydroxide ions to the water. Okay. So you can write down the net ionic equation, carbonate ions plus water, giving you bicarbonate ions and hydroxide ions. Okay, and then we also have another one, that is acetic acid, sodium acetate, I believe. So the next salt is sodium acetate. Sodium acetate 7.66. Now that is also little over 7, pH 7, meaning it's also basic. Let's see what's happening over here. 7.66 sodium acetate. So sodium acetate. Sodium acetate is NaCH3COO. Put sodium right there, the way it is attached. This is sodium acetate. Okay, so sodium acetate, what's going to happen, it's when it is in water, it is going to dissociate into sodium ions and acetate ions, CH3COO minus, that's the acetate ion, 1 minus. Okay, now we have a cation and an anion. Sodium ion, is it going to react with water? Remember, sodium is a cation from a strong base. It's not going to react with water. What about the acetate? Acetate ion come from a weak acid, acetic acid. So it is going to react with water. So as a result, when it results, what's going to happen? So this is acetate anion, which is now going to act as a base, going to take up a proton from the water and form acetic acid. Again, the water molecule HOH, this is going to take up a proton and then leaving a hydroxide ion. So it's going to form, so the bond here breaks, acetic acid and hydroxide ion. Now what's happening here again? Hydroxide ion is basic, right? So this is a weak acid. This is a weak acid and this is a strong base. So as a result, since the dissociation of the acetate ion or reacting the acetate ion with water, adding hydroxide ions to the solution, the pH of the solution is going to be greater than 7. So that is why it is 7.99. Okay, so the solution would be basic. And then the next one is sodium hydrogen sulfate. pH 1.68, very acidic, sodium hydrogen sulfate. So what's happening with sodium hydrogen sulfate? Sodium hydrogen sulfate. So this is going to dissociate into sodium ions and hydrogen sulfate. Again, the sodium ions coming from a strong base, sodium hydroxide, so it's not going to react with water. Whereas the hydrogen sulfate ion with water, HSO4 minus with water, what is going to happen? So here, water is going to take the hydrogen ion from the hydrogen sulfate and going to give you sulfate ion and hydronium ions. Okay, so HSO4 minus and water, so this is going to give you sulfuric acid, hydronium ion, let's say it's going to give you sulfate ion, SO4 2 minus, and this water molecule going to grab a proton from HSO4, giving you H3O plus, hydronium ions. So the hydrogen sulfate combining with water adds hydronium ions, which is an acid. That is why it gives you a very low pH, as pH 1.68. Okay, so that is how you're going to write your net ionic equation. Okay. Okay, so you can write down it over here. And then some properties of buffers. Let me erase this part. Okay. Now we're going to look at some properties of buffer. The buffer system selected sodium acetate and acetic acid. Sodium acetate and acetic acid is the buffer system. And the pH of the buffer. So this buffer has been made, and then you can dip the pH meter into the buffer solution, and the pH is going to be 4.42. So if you know the pH, how do you find out the hydrogen ion concentration? Which you guys already know how to calculate that. That is going to be pH equals negative log of hydronium ions, right? So then the hydronium ions H3O plus OH plus is going to be 10 base negative 4.42. So this will give you hydronium ion concentration, which you can write down. What is the concentration of hydronium ions? Okay. And can you calculate and see what number you're going to get? 4.42. You should be getting something like 3.80 into 10 to the negative 5. Check to see your calculator. You're going to get that number. 3.80 into 10 to the negative 5. Okay. And then the pKa. So the pH of the buffer is given, and then the pKa. So for the pKa, we can use that equation 4b, equation 4b, which is pH equals pKa plus log base over acid. Now when you mix this buffer, to make this buffer, when you mix the solutions, the molarities of the buffer solutions are the same, and also the volume was also the same amount. So as a result, the concentration of the base and the acid are the same. So in that case, pH is going to be equal to pKa. So the pH, which is 4.42, will also going to be the pKa of the buffer, 4.42. Okay. And then what you do is you add water to this buffer solution. So now you have a diluted buffer. pH of the diluted buffer is 4.56. And again, the same way you can calculate the hydrogen ion concentration like I showed you earlier, which you can do. So the pKa, again by dilution, we didn't change the concentrations of the base and we did change the concentration, but it is the same amount that is being changed. Okay, so the pH also going to be the same as the pKa for number 2 as well. Okay, and then to the same buffer add 5 drops of sodium hydroxide. So sodium hydroxide is a base. So by adding sodium hydroxide, you can increase the buffer pH a little bit, 4.66, 5 drops. And then the pH after adding 5 drops of HCl, 4.58. After add HCl, the pH drops. You can see that since it's a buffer, the pH is not going to change dramatically by adding 5 drops of strong base sodium hydroxide or hydrochloric acid. Comment on your observation in parts 1 and 2. And then the next part. pH of the buffer in which base concentration over acid concentration equals 10. So if you look at your part 3, that is going to be what are you doing in part 3 of C? It says make a buffer mixture containing 2 milliliters of the acid component and 20 milliliters of the solution containing the conjugate base. Okay. Mix and measure the pH. Calculate a third value for pKa. So since we are adding 2 milliliters of the acid and 20 milliliters of the base concentration, base volume, so the ratio between B minus and HB, which B minus is the base and HB is the acid, is 10. So you need to calculate the pKa of this buffer, the newly made buffer. So we can again use the equation pH equals pKa plus log concentration of base over acid, HA. Okay. So log 10. So B minus over HA, that is going to be log B over HA. So that is going to be 10. So pH is given to us as 5.71 and we don't know the pKa, and then B minus over HA is 10. So log 10, if you do the log 10 in your calculator, that would be 1. So then the pKa is going to be, as a result, 5.71 minus 1, that would be 4.71. You subtract 1 from 5.71. Okay. And then the pH after addition of excess sodium hydroxide. Now to this buffer, if you add 5 drops, it would change very slightly, just like the previous one, since it's a buffer, so it is in the buffer range. But if you add excess sodium hydroxide, it increases. It cannot hold any more sodium hydroxide if it goes above the buffer capacity. So then the pH will increase 11.54. Okay. And then you are making a solution with distilled water, your part 4. Under C, part 4 going to be put 25 milliliter distilled water into a 100 milliliter beaker, measure the pH. So the pH of the distilled water 6.99, which makes sense because pH is 7, should be 7, neutral in distilled water. And then measure the pH, we did, and you add 5 drops of 0.1 molar hydrochloric acid. 5 drops. So pH decreases to 3.31, about 4 pH units, right? Because in distilled water there is no buffer capacity, there are no buffer action. So as a result, pH drops, even adding few drops. Same with the sodium hydroxide. You add few drops, 5 drops, pH increases since it's not a buffer. Distilled water is not a buffer. Okay. Okay. And then the part 5. So part 5, it says select a pH different from any of those you observed in your experiments. Design a buffer which should have that pH by selecting appropriate volumes of your acidic and basic components. Make up the buffer and measure its pH. pH of the buffer solution to be prepared, let's say it's 5. Okay, and then the average values of pKa as found in parts 1, 2 and 3. So if you look at our part 1 pKa 4.42. Part 2 pKa is going to be 4.56, and part 3 pKa 4.71. So you will add all these three and you're going to divide it by 3 to find out the average value of pKa. And when you do that, you should be getting a number something like 4.56 is what I got, but feel free to check to make sure that the calculations are correct. Okay, average value for pKa, I got something like 4.56. And then the B minus over HB in buffer, the ratio of base to acid in buffer. What we want to make is pH 5 buffer. So how do we calculate the buffer ratio? We can use Henderson-Hasselbalch equation, which is pH equals pKa plus log concentration of base over concentration of acid. Now the pH is 5 and we found pKa 4.56 plus we don't know the ratio, log base over the acid. So 5 minus 4.56 is 0.44. So then the ratio is going to be 0.44. 0.44 equals log base over HB. Okay, so then we can find out the ratio 10.44. That is going to be 2.75 is what I got, the ratio 2.75. Okay, so the concentration of base over the concentration of acid ratio is 2.75. If you are going to use the same concentrations, for example, let's say 0.1 molar, 0.1 molar, so then these concentration terms are also same as the volume ratios. Okay, so let's say you want to make a buffer where you want to have HB, want to take 10 milliliters of HB. So how much is going to be the B minus then? I'm going to erase this part so I can write. Let's say B minus over HB concentrations ratios, and these concentration ratios are same as the volume ratios if we are using the same same stock concentrations. For example, if you are taking 0.1 molar base, 0.1 molar acid, so the volume ratios are going to be the same. So 2.75. Let's say you want to take 10 milliliters of this to make the buffer. So then B minus, the concentration, the volume of the base is going to be then 10 milliliters times 2.75. So the volume of the base that you are going to take is then going to be 27.5 milliliters, and then the volume of the acid that you are going to use is going to be 10 milliliters. So you take 10 milliliters of the acid, 27.5 milliliters of the base, you mix it together and then you measure the pH of the solution. That should give you the pH. But the data that is given here is a little bit different than what the calculations that I came across. But that's okay. That's fine here. They have used, it's the same concentrations, volume of 0.1 molar sodium acetate or any other anion, and then this is the base is a sodium acetate, and then the HB is the acid. So volume of 0.1 molar sodium B is the anion. They have used 19.5 and 10.5 and then got the pH of the buffer 4.96. Looks like their ratio, so these data I didn't do the data, thankfully. We appreciate that some lab techs did these not the calculations, but some calculations as well as all the experiments. So it looks like their ratio that they got is, let's see, 9 over 10.5. Their ratio is 1.85, but I got it as 2.75. So the ratio, I got this as 2.75. If it is 2.75, if we were going to make buffer solution, we will have to use the base component 27.5 and the acid component 10 milliliters. It looks like what they have got to get these volumes, the ratio is 1.86. That's the ratio they got. And how do we get this ratio? Again, by subtracting 5 minus 4.56. This is the average values over here, pKa, in parts 1, 2 and 3. Okay, so 2 is the distilled water. I just want to explain you how the calculations is being done. Okay, alright, I think that's about it. I'll talk to you later. Let's see if I remove the distilled water pKa, what value would we get? 4.42 plus 4.71. 4.56. Okay. All right, we're done.